Nucci, and I've been a safety engineer and consultant for over 20 years now. So when I decided to start my own business, I was wondering what I was going to call it. And I looked around at various names, some of which were already taken, and I came up with the name The Safety Artisan for the business and the website safetyartisan.com if you want to take a look. And I came up with that name because I liked the word artisan and what it meant and the connotations. So first of all, I mean, artisan means a skilled person who does something by hand. And it can also refer to a thing that is, specially handmade, usually with high quality materials. So I like the sound of that. And I think it's appropriate, even in this modern age where I've worked on, huge projects, multi-billion-dollar projects that lasted for years and involved thousands of people. Because even on a big project, we're still relying on individuals being competent to do a job and to know how to do it, and to have that skill and that awareness and that understanding. So that artisanship, that appealed to me. I thought that's good. And another thing was that there's this connotation of somebody working alone at home, maybe a sort of a cottage industry type setup that used to exist before the Industrial Revolution. Oh, I should say before the first Industrial Revolution. Now, whichever Industrial Revolution we're currently in at the moment, I don't know. But we've gone back to a world where, thanks to the internet, you can sit at home and do work. And in fact, thanks to, the recent global pandemic, more and more of us have been sat at home doing work, working remotely over the internet. And I, as an individual, can reach hundreds, thousands, or even millions of people over the internet with my teaching and with my knowledge and experience. So, the internet has really enabled a return to those kind of cottage industry ideals where individual people can do something of high quality and find a market for what they're doing, regardless of, big brand, big business, etc., etc. So we can, you and I can communicate one-to-one or one-to-many, and you can communicate with me, and we can learn together and share together what we want to do. Now, if that sounds good to you, if that sounds something that you're interested in, then please check out the videos and other learning products at safetyartisan.com. And you'll also find me, Simon Danucci, on udemy.com. So if you want to see what I do on a third-party platform, and then that's there too. Okay, well, thanks very much. And I look forward to seeing you again soon. Cheers. Okay, well, that's enough of that. Thank you very much. Hi, I'm Simon, and welcome to the webinar. It's good to see you. I say see you. I can't always see who's on. So can I just start off with a sound check? Can you hear me? So if you can hear me okay, somebody please let me know. So, I did one of these before, and I went on for about half an hour before I realized that nobody could hear me. but we should be okay. All right, well, I'm going to assume that we're doing okay because I checked the microphone before we started. So what I'm going to do, we're going to share, I've got some slides to share with you. And as it says, we're going to be talking about, oh, thank you very much, Stephen. It's nice to see you. That's great, so you can hear me. So I'm just going to share the screen, and here we go. So what we're going to be talking about tonight, because it's 5:30 here, it's getting towards dusk. But greetings to you, whatever time zone you're in. We're going to be talking about hazard analysis within a systems engineering lifecycle or framework. Okay, and I'm going to be talking about tasks 205, 204, and 209 from Mil-Std-882E. And as it says, it's a free webinar from the Safety Artisan. Now I'll crack on because we've got quite a lot to go through. So why should you listen to me? So, okay, 25 years of experience working on lots of different kinds of aircraft, ships, subs, air traffic management systems, a little bit on trains and cars, lots of software, and now lots of electronic sensors and communication systems and EW systems and all that kind of stuff. So lots and lots of different things. And I've been lucky to work on some small programs, which are great because you get to do everything. And also to work on some very, very big programs. And I mentioned Eurofighter and Future Sub. Future Sub didn't go very well. In fact, it failed dismally. But, you know, you get to benefit from my bad experiences and hopefully you can avoid them. And also I've worked in the UK. I had a good career in the UK. Moved to Australia about 10 years ago, and I've been doing safety work exclusively in Australia, pretty much. And I've also worked on a lot of US and European programs, as well as UK and Aussie. So I've got some fairly broad experience about how different countries and cultures do safety, which can be very, very different. And in terms of teaching and instructing, I was on the team that had the contract to teach all UK Ministry of Defence people safety for about 5 years. And I also created some bespoke courses for particular clients. And also got thousands of students online. And I've been lucky enough to present on several, well, safety and software topics at international conferences. So that's me. Okay, let's move on. So what we're going to be talking about is integrating hazard analysis within systems engineering. Okay, I say integrating it, fitting it together. I do like plain language. So we're going to talk about fitting it together. And as I said, we're going to be talking about 3 tasks today in this order, although you'll see that the order isn't necessarily important. So we're going to be talking about task 204, subsystem hazard analysis, 205, system hazard analysis, and 209, system of systems hazard analysis. And as you will see, what they've got in common is very tightly tied to the systems engineering framework lifecycle at different levels of abstraction. So that's what I'm going to talk about. And when I'm talking about the systems engineering lifecycle, we can use the V model, which is a very convenient shorthand. And the point of the V model and systems engineering, or one of their key points, is that very early on at the top left-hand side of the V, when we're developing our concepts and our requirements and our architecture and our design, at every stage, before we go any further, we're thinking about, well, how am I going to validate this concept in real use? How am I going to verify these requirements during integration testing, etc., etc. How am I going to prove the design? So from the very beginning, we're thinking about how we're going to demonstrate that we've done the right thing and done it the right way as well. And so that's what helps us to deal with huge complexity successfully most of the time, and to actually build better products. Because if we're thinking about how we're going to demonstrate that the product has met the requirements, then that's pushing that discipline onto us very early on. So we're probably going to get better results, okay, as well as being able to complete the job, quicker and more efficiently. And so that's the context, if you like, the systems engineering context, the life cycle, the model. Relate to it however you wish. So thirdly, in terms of explanation, we need to talk about these terms. What's a subsystem, what's a system, and what's a system of systems. So let's start in the middle. So we have a system that we are developing, or we're buying it, or we're assuring it. We're doing something with the system. And by a system, I mean a total package, not just hardware, but the software, the data. Do we need people to operate it and maintain it? What's the totality of the system? Okay, and then that system is something that is going to work. It's going to deliver value or benefit. It's going to do something on its own. Okay, it's enough to perform whatever mission or task or business goal we have for it. And then going to the right, we can break down that system. We don't always do so, but we can break down that system into subsystems. And maybe those subsystems, maybe we're going to buy them from a vendor. They're going to develop something for us, or maybe we're going to buy something off the shelf, or maybe we're just going to put stuff together with bought components and maybe some software to glue it together. And whichever we do, okay, we're thinking about maybe like we might have a control subsystem, we might have a power subsystem, we might have, a sensor subsystem, we might, whatever, propulsion, who knows. So, so we could have more than one subsystem, and typically we will have a specification for what each subsystem is supposed to do. Okay, not always, but typically. But we have some expectation somehow of what we need from each subsystem for the whole thing to work properly, or we should do. If we don't, we're probably in trouble. And then the sort of system of systems thing, okay, typically we want a system to operate with other systems. We've built an airliner, but we want it to fly in controlled airspace and work with air traffic control, etc. And it's got to work in the real world environment. And then maybe the tools at the top, maybe we've got a support system as well to keep the system functioning and available. So that's the definitions that I'm thinking of. So they're not theoretical. There are theoretical definitions of all these things. You can look them up. You can Google them. I'm interested in a practical, pragmatic expression of what we're talking about, okay, in terms of what works. So that's the basis of what we're talking about today. So first of all, I'm just keeping an eye on the time. Okay, we're going a bit faster than this morning, which is normal. First of all, I'm going to talk about subsystem hazard analysis, which is task 204 in Mil-Std-882E, which is a US defense standard for system safety. But to be honest, the principles that you'll find in 882 are very common in other standards and in systems engineering in general. So Mil-Standard emphasizes requirements very much. And of course, when we're looking at hazards, what could go wrong? So
we want 204 to do a number of things. We want to verify that the subsystem complies with its requirements, that expectation of what it needs to do. But with the system safety focus, we're thinking about the requirement to eliminate hazards and reduce associated risks. Okay, and this task is probably going to identify new hazards that we haven't thought of before, associated with the design of this subsystem. And we're doing it for a purpose. We're doing it to recommend useful, necessary actions to eliminate those hazards, or if we can't eliminate them, to mitigate their risks. Okay, so we're doing it for the purpose of risk reduction. It's not a theoretical exercise for its own sake. So that's SSHA. And I've got a few comments on SSHA. This is just an overview. I do a lesson on all of these things, and they're all about 45 minutes to an hour. This is just a brief overview. But I wanted to mention the task asks us to consider performance and degradation of performance, functional failures, and errors in timing, design defects, which might be in there from manufacturing, or design defects, and inadvertent functioning. Now, the functional stuff we typically might address by doing a functional failure analysis, or if we've got a design, we might do a FMEA, a failure modes effects analysis, or a FMECA, a failure modes effects and criticality analysis. But the simplest one is the FFA, where we just think about no function, so it doesn't work when it should. It works when it should not. Okay, and it works, but it works incorrectly. Okay, and typically we're good at physical hazards. Okay, it could catch fire, it could poison somebody, it could fall on somebody, you could burn yourself by touching it, whatever. We're not so good at doing the functional failures, and when we do, we often do no function. It doesn't work at all. What happens? We don't always think about the other two, the inadvertent and the incorrect function, but they're actually much more insidious and dangerous failure modes. Okay, so we want to do that. We might use those techniques to identify hazards, and also to look at not just at hazards, but investigate performance and non-compliance issues. What happens if it goes wrong? If we have a non-compliant system, let's say, well, how do we avoid that, or what do we do about that? How do we recover the system back to a safe state? So we should be thinking about all of these things, and there's a variety of techniques that we can use. So that's the first point I want to make. The second point is that we need to include the human, because almost always, I know autonomous is an AI is a big buzzword at the moment, but the reality is very, very few systems are completely autonomous, if we're honest. And even those that are often need humans to support them and fix them. And they have to be designed by a human and understood by a human and tested by a human, and so on and so forth. So we need to include humans. So we need to think, okay, how could the system, induce a human error or erroneous human behavior, and vice versa? Could the human do something that misdirects the system, etc.? So we could use a hazard and operability study to think about that interaction. There's other models we can use. 5M and Shell they're quoted in the standard, I think, or in the FAA handbook. But there are a lot of other human factors techniques, much more modern. And in fact, if you're interested in that, we talk about the basics of human factors, myself and my friend Peter Bender, in a lesson which is free on YouTube. The link is in the chat. Okay. If you can't see the link in your chat, then please send me a message, and I will put it in Facebook or LinkedIn or whatever. So that we need to include the human, point 2. And point 3, okay, if we're going to do compliance checking, which we should, then we need to be assessing that subsystem spec. Maybe we can, use some safety techniques to examine the specification. We need to look at, what do we need from an interface as opposed to maybe what are we actually getting, required versus provided, and what derived safety requirements have we got. So for those who aren't familiar with derived safety requirements, they are often, but not always, controls for hazards. So we do some safety analysis and we go, okay, this thing could go wrong in this manner. What controls can we put in place to manage that risk? Or it might be a performance issue. We now understand that, okay, this subsystem has got to work. Let's say it's got to have an availability of X% in order to achieve an overall satisfactory result. Just excuse me a second. Sorry about that. And very often we're going to be assessing documentation from suppliers to do that. So, or I say documentation, assessing the product either in reality or virtually. We might be looking at training materials. We might be looking at manuals, brochures and feature lists, and warnings and cautions therein. So we're going to be interrogating the subsystem, the product in some way to try and assure ourselves that it's good enough and safe enough to use. So that's a little bit about subsystem hazard analysis. By no means complete. I don't claim this is complete. I'm just giving you a flavor of what we're talking about. So let's move on to system hazard analysis, task 205. And 204 and 205 interrelate very strongly and are very similar. Okay. And so for 205, we've actually got the same 3 purposes as 204. We've got verify subsystem compliance, identify hazards, and recommend necessary actions. What we've added is identifying hazards from the integrated system. So we've taken all the subsystems, we've bunged them all together, we've mashed them together, and what emerges, what behavior emerges, what hazards emerge from the integrated system, because it's not always predictable. The sum is sometimes more than the whole is sometimes more than the sum of the parts. It's not just that kind of exercise. So task 205 is similar but different to 204. And in fact, on the 204 and 205 lessons, I spend quite a lot of time talking about the differences and the different emphases of the tasks, because we're doing kind of the same thing, but for slightly different purposes. And with that in mind, we don't necessarily just do 205 after 204. The numbers kind of imply that. Some of the words in the standard imply that, but I think that's a mistake. We're missing a trick if we don't do 205 early, because what we need to do is set and understand our requirements at system level before we decompose down to subsystems. Now, and even in the case where actually most or all of our subsystems are commercial off the shelf, we still need to understand those interactions, okay? And we still need to understand the safety implications of system performance in order to understand what the subsystems must achieve, okay? So even if we're not developing them, we're looking for a certain performance level or certain features in a subsystem that we're going to buy. So we want to, when we're going top down on the left-hand side of the V, we want to do some 205 before we get into subsystems. And then we also want to do some 205 when we're going up the other side of the V on the right-hand side. So we go early in order to gain insight and influence and to set requirements. And then we also, check compliance towards the right-hand side as we complete our life cycle. Okay. So even with the one task, different emphases at different points in the life cycle. As I said before, differences between 205 and 204. With 204, we're often emphasizing a self-contained subsystem and the internals thereof, if we can, or maybe we can't because we bought it and it's a black box to us. So we've got focus on externals. We need to think about what we're trying to achieve with these tasks at what point in the life cycle, and then that will affect what techniques are appropriate to use. Okay, so we might be using an inductive technique where at the start where we're using our imagination and saying what if, whereas on the right hand side we might have a bunch of results and we've just got to check through a long list of requirements that have been met, test results, whatever it might be. So it might be a much more deductive where we go through all the data and assess where we are. So again, different emphases. Now, really, in the ideal world, the client and the end user community should do a bit of task 205 early, okay, or maybe they delegate it to the prime. The customer hardly ever does this, but they really should understand the system they're trying to buy or trying to use or specify. And a bit of modeling in that area can really help. And in fact, that was a big part of of what we did early on for the submarine program, and in fact for many very complex, closely coupled systems, actually to develop a robust set of requirements, you actually have to do a lot of modeling and really understand the implications of your requirements on the vehicle in some detail, okay, to deal with that amount of complexity. So sometimes you've got to do some design to come up with some requirements, dare I say. So yeah, the customer, the end user should be doing some 205, but almost always 204 is delegated to the prime, and maybe the prime gets the subcontractors to do some work if they're doing development. And understanding the differences between these two complementary tasks is often the key to success with a designed product. Okay. Right. So that was 204 and 205. We're now going to make a bit of a jump because 209 is a bit different. Okay. So we're going to the system of systems. And the purpose of the system of systems, or the SOSHA, if you want to shorten it a bit, is to identify those hazards that emerge at the system of systems level. And maybe we'll need to come up with some special requirements, again, to eliminate the hazards or mitigate their risks, which would not exist if we were not putting these systems together. So, for example, I mentioned airliners and air traffic control. Okay, well, if we didn't have an air traffic control system interacting with the airliners, then it couldn't go wrong, because normally it's supposed to keep the airliners apart, but maybe the ATC system could go wrong and put them together when it's not supposed to. So that's a bit of a wrong way round example, because we introduced ATC systems to keep planes apart. But we did it for a reason. There was an implicit system of all these planes whizzing around the sky, but it wasn't managed. So we've now introduced an air traffic control system to explicitly manage the system of systems, which was always there but not appreciated. So I'm actually going to talk about this by example, because back in 2006, one of my very first jobs as a consultant was to do a SOSHA safety case. And what we were asked to do was to assure the safety of a system of systems. So we've got an aircraft, we've got an aircraft carrier, and we've got some systems or some equipments that are being purchased and upgraded as part of a system in order to put the two together in the right way. So we want the aircraft to make it back to the aircraft carrier before it runs out of fuel. and get down safely, even in bad weather. Okay, and to do that, we had to take into account the humans in the loop, because we have radar controllers and we have pilots, the operating environment, which can be quite unfriendly and unhelpful. We have operating procedures, and also we have maintenance and management. So quite a lot of different things to consider. And here's a nice little picture with some icons, which hopefully disguise the actual project. So we've got a ship, we've got planes and pilots, and we've got a radar and some other stuff, and a radar operator. I think that's actually an icon for a disc jockey, but it'll do, you know, for somebody looking at a scopy. So we've got those three elements, and they're all interreacting, interfering sometimes with each other, and we need to sort of say, okay, does it all work together safely? And so, for example, in this case, we came up with a solution, and this, by the way, is in goal structuring notation. This purpose of this is not to teach you GSN. It's just an illustration. So at the top, our goal is that we want this system to be adequately safe for aircraft to locate the ship and get close to it, close enough for the pilot to do a visual landing. So how did we do that? Well, in this particular case, we decided on a strategy of, we'll look at all the elements and say all the elements are safe and all their interactions are safe. So if all the elements, if all of the different systems that already exist, by the way, or at least two of them did and have been in use for a long time, even some of the new system had been used before and elsewhere. So we needed to show that all three of those major systems were safe in their own right and that they worked together, they played nicely. And so what we did is, you know, are these equipment safe to operate? Because of course this isn't just a technical exercise in terms of reliability, but are they actually safe to operate? Is the whole system of systems safe in operation? Have we met all the safety requirements? Because, you know, there are implied safety requirements between the three systems, because, you know, the pilot is assuming that he or she gets the correct instructions from the, you know, the air traffic controller who's talking them towards the ship. And then finally, are all of those physical and electronic and so on interactions safe? And which again is not necessarily obvious just looking at things in isolation. So, and then underneath that unpacks much further into a much more complex safety argument. But it just illustrates, I think, the kind of things that you have to think about with a SOSHA. Okay, and hopefully that is more useful than talking in theoretical terms. Okay, and no disrespect to people who love their systems engineering theory. That's all good and proper. But if we're trying to understand something, I think an example and a few pictures go a long way. So that's me. I've banged on for just over half an hour now. So next steps, I've given you an overview of those three tasks and how they fit in. But let's look at some more resources for you. And again, all of these things are in the chat. So the links are in the chat. If you can't see them, again, message me. Either message me now or I'll let you know if I get any messages. If you've sent me a message and I say I haven't seen any, then message me either at admin@safetyartisan.com or go to the website and do a form submission on the contact page, or, you know, contact me via social media. Okay, so I've got a few relevant things that you might want to look at next. So system safety concepts and principles, that's the really basic stuff. That's free, and you can find that those videos that you can look at anytime there on the website. What is system safety? Again, my thoughts on system safety and system engineering. Again, that's free on the website. System safety process is actually a paid course. That one's $45 US. And then human factors I already mentioned. That was a sort of an hour-long chat with Peter Bender introducing human factors. And I've worked with Peter, great guy, really practical, useful approach to human factors. Really saved my bacon on a very difficult project. So I'd highly recommend working with Peter if you can, or just listening to him. And you can do so at that link on YouTube, again for free. And then finally, that link at the bottom is for email subscription to my email list, which again is free, no commitment, no purchase necessary, but you will get updates from what I'm doing, the stuff that content that I'm pushing out. And also you'll get some access to some freebies and some big discounts on the paid courses. So little plug there for the Safety Artisan, but hopefully some stuff that you will find interesting, and you can get a better idea of where I'm coming and what I do. Yeah, and as it says, there's the website, safetyartisan.com. If you want to get in touch, admin@safetyartisan.com, social media or whatever. Lots of ways to do it. Leave me a comment. Okay, so that is the last of a series of 5 webinars on Mil-Std-882 that I'm doing. And I just wanted to let you know that what I'm now doing with all that content, the existing content and the new content that I've created, is putting that all together into some mini courses. Okay, so as we had 5 webinars, we'll have 5 mini courses, and those courses between them will cover all the analysis tasks, the 200 series tasks. Okay, apart from task 210, which is environmental hazard analysis, and you can get a lesson on 210, but I'm going to leave that one to one side, I think, whereas I think it's more helpful to think about the safety stuff in slightly bigger handfuls rather than thinking about one task in isolation. Okay, so those will be the 5 mini courses that will come out, and I'm aiming to push out 5 ways to identify hazards, which is what starts us all off, on the 1st of September, which is the 4th anniversary of the business. So I'm looking forward to celebrating that with you all, with some discounts and giveaways. In the course, you will it will be on a full-featured learning management system, so not just downloaded videos, but I've chopped up the videos into short sections of no more than 10 minutes, so you can access a little bit at a time, whenever suits you, maybe on your mobile device. There will be quizzes and assessments, there'll be email support, and part of the price of the courses will be community support and monthly Q&A sessions with myself and interaction with other members of the community. So I hope that people will find that more helpful and more supportive than just the recorded videos on their own. Okay, so we've done Q&A. So I'm now going to stop sharing, and we're going to have our Q&A session where you can ask me questions about what I've just talked about, or indeed anything you want on safety. And in fact, this morning I got a curly one on common safety method, which is a Euro approach to rail safety, okay, or rail and other guided systems, or ROGs as they're called. And I'd never heard of common safety method, so I had to go and look it up, and we had a chat about it. So I don't have all the answers, but I can usually go and find them or talk to somebody who has got relevant experience. So do we have any questions, please, either in the private chat, if you booked via Eventbrite, sorry, or via social media. So if you're on YouTube or Facebook, you should be able to see those links. Maybe not on LinkedIn, it doesn't always work, or on Twitter. So if you're on LinkedIn or Twitter and you've submitted, well, in fact, if anybody, let me just check, I'm not seeing any comments yet, apart from Steve saying that he could hear me. So I'll let you think about some curly questions and type away. I'm just going to wet my whistle. It's water, by the way, not gin. I'd just like to point that out. Right. So just to reiterate then, while you're waiting, we've got all of these links. So we've got the email subscription, the human factors. Oh, right, we've got the human factors twice. So good we shared it twice. System safety process, concepts and principles. Yeah, so it's all there. And as I say, if you can't see it, I will go and add those things to Facebook and to LinkedIn right after this. And I'll add them to the morning session as well. I'll also be sharing this video because it's recorded. I'll also be sharing this video with those who signed up but couldn't make it, and of course it's also on the social media as well. So you can always look again. And I tend to put a processed version on YouTube as well. In fact, this morning's session is already published on YouTube. All right. Well, thank you very much. Thanks for that lovely comment, Stephen. And thank you one and all. So if I have no more questions, we'll wrap it up, and just remains for me to say thank you so much for joining in. And I look forward to seeing you. I will be doing more webinars, but I look forward to seeing you either in the safety community or at further webinars, or indeed, on social media or wherever.